Hey guys, so we're going to look at doing our part 3 of our notes today, and we're on our notes packet. If you're doing the printed out packet, we're going to be starting on page 10. Slide 32 is where we left off. You can also type it straight onto the notes that you've been doing if you're using the Google Doc, and follow along that way. And the other thing you can do is just copy down the notes and take pictures of hand done notes as well. So today is looking at, if you pull out your Learning Targets worksheet, Learning Target E, which says describe how the cycling of energy and matter has changed throughout Earth's history. We're going to talk about age of the Earth, a little bit of carbon cycle, not so much about cyanobacteria on this go around of it. We're definitely going to spend some time talking about ocean pH, in particular ocean acidification, and the human impact on Earth's systems. And in particular, we're going to look at fossil fuels. It's not going to be as much as previous years, but we're going to touch upon it a little bit. Most of this will be, most of the human impact will be in class, as will ocean pH. Okay, so we are on slide 32. It looks like this in your packet, and let's go ahead and get started. So, all right, Earth's history and the cycling of matter and energy. We know through various means that the Earth is about 4.5 billion years old. Some of the evidence that's been collected to let us know the age of the Earth, that's helped us figure it out, is we've looked at meteorites, we've looked at moon rocks, we've also looked at some of the oldest rocks and minerals on Earth, and have done some radiometric dating, which we'll talk about on the next slide, to determine the age of those. And the oldest materials that we can find is about 4.5 billion years old. On here is a picture of radioactive decay and what that means. So you start off with an element here which is 100% of the same kind of atom, and this is the time down here, and this is the percent of particles or atoms that have changed. So if you have uranium, 100% uranium here, at this many years, half of the uranium has been turned into lead. And we'll talk more about that when we do, or we're actually going to watch a little video on that too. But that's what a half-life means. Half of it gets converted into something else. Radiometric dating uses that because it's a process of determining the age of rocks from the decay of their radioactive elements. So you're gonna, while we're watching this, think about what role does uranium play in this process. So let's go ahead and click this open. And we have to scroll down a little bit, make it full size. It's only 1 minute and 38 seconds.
Now, normal background radiation sounds like this. But this rock is a little more interesting. And it's this rock which turned out to be the clock, which allowed us to date the Earth.
The rock contains uranium, an element that loses subatomic particles over time. Those losses change uranium into other elements with fewer particles. It's a process known as radioactive decay.
If you leave uranium around for years, it all turns into lead. But it turns into lead a little bit at a time. So you can measure the rate at which it turns into lead. Once you know this rate, which is not hard to figure out physically by watching the process happen in real time, you can go to a rock sample, break it open, and measure the relative amounts of different kinds of lead and uranium in it, and determine from this how long it's been since the rock cooled.
This was a phenomenal discovery, and in the very earliest, most simple attempts at it, it was discovered that, in fact, the Earth had to be an order of magnitude older than previous estimates had argued for. And the average looked like it was about 2.5 billion years at that time.
Ultimately, rocks are found that are 4.5 billion years old.
Okay.
Now, Now, normal background radiation.
Start over, sorry. All right, so let's go back to the notes. So what role does uranium play? So hopefully you wrote down something about it being like a clock. It kind of is used to date how old the Earth is. That's one of the elements that we know exactly how long it takes, what its half-life is for it to turn into lead. So we can pretty accurately measure how old something is. So, okay, so let's talk about what the early Earth looked like about 4 billion years ago. We'll give it 500 million years to cool down a little bit. The earliest Earth, so we have 3 atmospheres when we talk about Earth's atmospheres. We have the earliest atmosphere, then we have the early atmosphere, and then we have our current atmosphere. Now, our earliest atmosphere was made of hydrogen and helium, but those are really light gases. When you look on the periodic table, they are the lightest 2 that you can have. They have the smallest number of particles, so they only have 1 or 2 protons, neutrons, and electrons, depending on which one you're talking about. Those are very hard they were very hard for the Earth to hold on to because they didn't have enough mass for the pull of gravity to keep that atmosphere around our Earth. So what happened is they floated off into space, and the earliest Earth lost its atmosphere. After that, somehow carbon dioxide became very prevalent in our atmosphere, most likely due to volcanic outgassing that was occurring. So there was lots of eruptions. It was a very volcanic period of Earth's history. And with that, there's water vapor and carbon dioxide, ammonia, and methane being released, but they are heavy enough that they were able to be to stay and stick around Earth. So that became our early, not permanent, but early atmosphere that was able to stick around. Please note there is no oxygen in this early atmosphere, so we could not have life as we know it. But it's important to see that it is mostly carbon dioxide, which is really important because we look at organisms like the cyanobacteria, who were then able to take the carbon dioxide and through photosynthesis convert and make oxygen in our atmosphere. Through billions of years and that process of photosynthesis, we now have a different composition of our atmosphere, and this is our current atmosphere. Make sure you copy this pie chart down. We have 78% of our atmosphere is nitrogen, so the bulk of it isn't even oxygen. 21% is oxygen, and then 1% makes up everything else, including the carbon dioxide that has been such a big component of our climate change problems. So it doesn't make up very much of our atmosphere, but it certainly has a very huge impact in what's going on with weather and climate around Earth. So make sure you write that down, copy the pie chart down. Okay? If you need to pause, go right ahead. So how did the atmosphere change from the carbon dioxide rich atmosphere to our nitrogen rich and oxygen atmosphere? So first of all, early Earth was very hot. That's because I pushed the button. That's because it did have lots of volcanic outgassing. Slowly over time, the Earth began to cool, and as water vapor cools, it condenses. So everything that was gaseous in our atmosphere condensed, became liquid, which caused torrential rains, which we believe led to the formation of the oceans, or partially led to the formation of the oceans. Another contributor, the believed contributor, is comets that were made of minerals and water. As they struck Earth, they may have also contributed to the formation of oceans because the water in it's kind of made of ice more than water. So as it was exposed to the warmth of Earth, it melted, and then we had the formation of the oceans. Once the oceans formed, life as we know it could begin to flourish. Okay? So what we're going to do now is you're going to pause the video after I finish giving you your instructions, and there's a separate PDF of our Biozone book that you do not have, but I went ahead and made scanned copies of for you. You are going to use pages this side, I did the wrong side, pages 106 through 107. You're going to read through them and answer the questions. There's questions 5 through 8. And there's room in your packet to answer the questions. Some of them they probably needed a little bit more room than I gave you, so I apologize. I'll make sure I change that for next time around. But make sure you understand we're going to look at photosynthesis and iron. In particular, there's banded iron formations, which are really important and a huge clue as to when oxygen became present in our atmosphere. I would suggest reading page 105 as well, because it's kind of interesting and it looks more in depth at that graph of carbon dioxide at Mauna Loa in Hawaii that we talked about at the beginning of our unit. So there's some information on there. I'm not asking you to do the questions on it though, so don't worry about that, but you want to read a little clip through it. It's kind of interesting. It explains the pattern, the seesaw pattern that we see a little better. Okay, once you have finished the questions on pages 106 through 107, then on page 12 in your notes packet, it says to outline biozone pages 108 to 111. Make sure you include any graphs that may be significant. So you're going to start with page 108, and I'm going to flip this over to make, there we go. Start with page 108, looks like this. Okay, do some outlining here. There's bullet points. I left you bullet points, kind of one per arrow, to kind of summarize what the bullet points are, and I'm showing you what I copied down for, but that's okay. And then on page 109, I put the topics, so I did put the topics for you so you could see where the explorers is typically the topic for your outline, and I copied down the chart here for you, the outline of it. You're going to have to, I filled it in, you're going to have to copy the chart that's in here, in there onto here, so you can do that and label when, and you'll be able to see when cyanobacteria became present, and that was quite a while ago, over 3 billion years ago. Okay, and then there's some more outlining to do through page, sort of the coevolution of Earth's systems. That's this big one. There's lots of bullet points there for you. Okay, and then there's a little tiny bit more information on page 111. There's not that much reading, and the outlining shouldn't take you horribly long if you go through it. And then I put the question that's on here is in your notes packet as well. So we're going to go ahead, and it says using the evidence in this outline and your understanding of photosynthesis and cellular respiration, including energy yields, which means you're going to have to talk about ATP and which processes produce that and how that's relevant to the formation of Earth. You're going to present an argument with one or more reasons for the coevolution of life and Earth's other systems. Notice how much space I gave you. I am expecting a decent size answer for this, or explanation. So make sure that if you make this claim, you have your evidence for it and your reasoning for it. Okay, so I'm looking for claim, evidence, and reasoning on this one. Okay, so go ahead, pause your video now, and you'll come back to finish the notes after you finish doing those pockets of notes. Okay, I'm going to switch back over to the notes now. All right, so hopefully everybody finished doing that, and we will be talking about that in class next week after the notes are due. Okay, wrong way. Carbon cycling. So carbon is the 4th most abundant element in the universe. It is also the 15th most abundant in Earth's crust. I'm not expecting you to remember that it's the 15th most. I would expect you to remember that it's the 4th most abundant in the universe. It's a pretty common element to find. Now, carbon is a pretty special element because it can form 4 stable bonds with other carbon atoms, or not just with carbon atoms, with other elements. That's what makes it so unique. So carbon can bond with hydrogen. It will bond with oxygen. It will bond with I just lost it. Nitrogen. It'll bond with lots of other elements, which means it can make lots of different molecules. Okay. The really important thing though is that it does also bond with oxygen, which we talked about because that's what makes up CO2. Okay. We also find carbon in all the different spheres in many different forms. So we have it in carbon dioxide in our atmosphere. We have it in carbonic acid in the oceans. We have it in limestone rocks in our geosphere. We have carbon in our bodies as one of the building blocks for our DNA has carbon in it, and it's in the glucose that we have. It's in everything that we have in our bodies has carbon as a main backbone, which is why when you get to college, if you take chemistry, you'll take an entire year on organic chemistry, which is all about carbon. So it's a very important molecule, and there's lots of study on it. So, or atom, rather, element, whatever. And this is what its electron structure looks like. I think it's a Lewis dot diagram. And the little dots are the electrons. Okay. All right, let's look at this picture of the atmosphere carbon store. This should be very familiar to you by now. We've seen this picture multiple times. We have fossil fuel emissions, which is burning up coal, oil, and gas, which is stored carbon. We have carbon stored in limestone and dolomite. We have the ocean that's storing it. We have biomass that's storing it. We also have ways that carbon dioxide or carbon gets out. So through diffusion, it actually can go back into the atmosphere. It can go from the biomass through respiration and composition and burning of fossil fuels, which is combustion. Okay. So hopefully you remember some of the carbon cycle stuff we've talked about, because now we're going to use that diagram and the stuff you've learned before, and you're going to fill in this table. You're going to identify the carbon sources as well as the carbon reservoirs. Make sure when you identify something as a source or something that's a reservoir, which means it's storing it, if it's a process that does that. So if it's a process that produces carbon, underline it. If it's a process that removes carbon from somewhere and stores it, underline it. Okay? Pause the video. Take a few minutes to fill this in, or a few seconds, and then I'll show you the answers. All right, so hopefully you got something like this. Sources would be your fossil fuel emissions, things like combustion. We also have decomposition and respiration. All three of these are processes. Okay, some of them are natural, like decomposition and respiration. Some of them are man-made, like combustion. Looking at reservoirs, we have the atmosphere holds a lot of carbon dioxide. So does our ocean. So our hydrosphere holds a lot. Our geosphere holds a lot in limestone and the dolomite. And then biosphere also holds a lot. Not as much as ocean and atmosphere. Processes that store carbon, photosynthesis, brings in carbon dioxide and converts it into glucose. And then diffusion is another process. It removes carbon dioxide from the atmosphere to store it into the ocean. Okay? All right, so looking at the next page, we're on page 16 of your notes. What happens with all the carbon in the ocean? Does it just sit there? Well, we wish it did, but no. In this picture, I'd like you to copy down the names of what each of the molecules are. So you have atmospheric carbon dioxide here. We have aqueous carbon dioxide, means it's dissolved in the ocean water. So it's with water. It's not bonded to the water because there's no lines in between, but it's mixed in with the water. Okay. Then when we have water interacting with carbon dioxide, carbonic acid forms. So put that as your label. Now, when carbonic acid forms, hydrogens can pop off of the oxygen molecule. They'll leave, right? So they get freed, and you get bicarbonate. Once both hydrogens from the water molecule, the two water molecules, gets freed from the molecule, you're left with carbonate. Okay, I'm not going to expect you to remember all of the details of this. I just want you to work through the process and know that each step has a different name because each thing is a different molecule. So this is not bonded together. This is it bonded together. Okay. Now we're going to look at ocean acidification. Okay, so there are some videos we're going to watch, or a video we're going to watch, and you're going to answer some questions that will help make sense of what ocean acidification is, why we should even be worried about it. So we have these pictures here of coral reefs, and you'll understand the coral bleaching effect here. And this is bleached, and then we have these little shells that sea snails shells that are not, they're deformed. So we'll talk about that after we watch the video. So I'm going to turn mine off and turn this up. Go.
Ocean acidification is a process that has also been called the evil twin of global warming. It's a problem that carbon dioxide in the atmosphere is causing because as the carbon dioxide dissolves in seawater, it forms a weak acid. It's not a really strong acid, it doesn't really do anything to us, we don't feel it, we don't feel that it burns our skin or does anything like that. But it is important for marine organisms because marine organisms that try to secrete calcium carbonate shells, like clams, like snails, corals, even some fish and some crabs, they try to secrete these shells, and it makes it a lot harder for them if the water is a little bit more acidic. So the reason why we know that the oceans are acidifying is that the actual act of forming this acid is a very simple chemical process. So if we dissolve more carbon dioxide in the ocean, we can calculate what the change in acidity is going to be. So on the one hand, we can calculate it. On the other hand, we can also observe it. There are some snails, planktic snails, they're tiny little, beautiful little shells. They look like butterflies. They're made out of a form of calcium carbonate that is called aragonite. And this aragonite happens to be very, very soluble in seawater, and so it's very vulnerable to acidification. In the high latitudes where the water is cold, the ocean sucks up a lot more carbon dioxide than it does in the tropical oceans. And so these snails actually experience a lot more acidification than in other places. And it turns out that these snails are a major food source for Pacific salmon. And so if the Pacific salmon cannot feed on those snails, then the Pacific salmon might actually disappear at some point. So all of this has effects in the end for our food chain, and that is what we're concerned about. But we have observed these changes already. So we have observed that the oysters hatch, but they cannot secrete their first little shells. We see that these pteropods, they're growing thinner shells, and the shells are malformed. We're seeing that in many plankton organisms. We see it in sea urchins. We see it in crabs. We see it in a number of different organisms. All of them are secreting calcium carbonate shells, and they're having a hard time to make their shells. We have time periods in Earth history where the acidity of the seawater has changed, whether it was due to massive volcanism or whether there are any other carbon impacts that have changed the carbon dioxide concentration in the atmosphere. And we can study those times, and with those times we can then see how the ecosystem was behaving, how acidic it got, how the temperature was changing at the time, how warm it was. So understanding how the system behaves in the past allows us to understand what we're doing today, and depending on what the projections are for the warming and for the carbon dioxide levels in the atmosphere, we can make better predictions of what that means for the seawater chemistry and also for the organisms that live in that seawater.
Okay, so sorry about the dogs barking. Okay, so number 7 is not in there in the video, but what do you think might be different about today's ocean acidification? So because this has happened before, how is this different, do you think? Write this down, and then I think this will probably wind up being an opener or some sort of discussion question at some point. So we can have a nice conversation about this, okay? It's kind of important that you understand that, yes, it's a natural process, but there's something different about what's going on right now, okay? All right, so let's look at the process of ocean acidification. So first of all, we have carbon dioxide that is being absorbed from the atmosphere by the oceans. So carbon dioxide from the atmosphere is being absorbed by the oceans. Once it gets dissolved into the water, it's going to bond with water and form carbonic acid. This results in a pH that is lowered for the seawater. So the lower the pH is, the more acidic it becomes. And 7 is neutral, and normally we would have a whole discussion on pH. Sorry about that. But 7 is neutral, 1 is the most acidic, 14 is the most basic. So we're seeing a small shift in making it lower. It's not changing by the whole number. It's not going from 7 to 6. It's tenths of a change. So from like 7.4 to 7.2. Okay. then after we have that, the hydrogen ions, so that's where those hydrogens were bonded on that picture before, and I said they get released. They're released by carbonic acid to make carbonate, okay, to then form bicarbonate. Okay, carbonate concentrations are decreased, so there's less carbonate, making it difficult for calcifier species to form calcium carbonate. So they need that carbonate in order to form their shells, but that carbonate is getting turned into bicarbonate, which means they don't have it available to make their shells. So instead of building their shells and then spending all their energy on reproducing, they're continually trying to build their shells, the young larvae, and they can't. They're getting deformed. They're getting very, very thin. So sometimes they can form them all the way, but then they stay super duper thin and fragile. So a lot of them are not surviving, which, as we saw in that last video clip, that's important because the specific salmon rely on these organisms, some of these organisms, for their main food source. So if they don't have a plentiful supply of it, that is ultimately going to move up the food chain. You're looking at a primary producer, or primary consumer rather, like the zooplankton. It's considered one of the zooplankton. So remember our food webs, we have the phytoplankton and then zooplankton, and then higher up we go. Salmon would be higher up. If there's not as much on that secondary trophic level, then that tertiary trophic level doesn't get as much energy either, so it can't support as many organisms. So this is ultimately going to affect larger organisms even than salmon, because then less salmon, and the bears rely on salmon. What's going to happen to the bear population? Don't know. Time will tell. Whoops, too far back. So this is the process. Hopefully you got all that. Then this is going to look at the graph that I showed you in the notes packet, or the Biozone. I said that it took a closer look at it, so we're actually going to talk about it right here too. So what trends do you see? Hopefully what you see, so we're looking at atmospheric carbon dioxide is the red line, seawater carbon dioxide is the green line, and the blue line is the pH. So, and it says in situ, and on your notes packet I put down in situ measurements require that the instrumentation be located directly at the point of interest and in contact with the subject of interest. So if we're looking at seawater, this means this instrument that's measuring this is in the seawater, okay? Same with this one, because it's a different instrument, it's measuring pH instead of parts of carbon dioxide. It's going to also be in the seawater. So hopefully what you're seeing is, or what you're noticing is this upward trend that there's more atmospheric carbon dioxide in the atmosphere. So more carbon dioxide in the atmosphere is leading to more carbon dioxide in our oceans. So more of it's getting absorbed, still not enough to bend that curve, as we hear for COVID. You know, they always talk about bending that curve. We're not bending the curve in ocean or atmospheric CO2, and we're just seeing a steady rise, which we're also then seeing a steady rise in the amount of carbon dioxide in the oceans, specifically in near Hawaii's Mauna Loa. What you also should see is not only is the CO2 level increasing in the ocean, as it increases, there's a decrease in pH. So remember I said 7.4 or whatever. The ocean pH is actually, looks like it's about 8.1 or so, and at the most it was just over 8.13. Okay, so it is on the basic side. It's even more basic than neutral, but it's becoming more neutral, and then ultimately, if that continues, more acidic. So it's definitely getting more acidic, but it's just getting more neutral. So we go from 8.13 down to right here, 8.08. So we're only looking at 0.05 of a change, but that's a significant, look at the loss of shell formation in just that 0.05 change in pH. And we're seeing that drastic of a change. So can you imagine what it will be in the future? Okay. So let's look at the next thing here. some causes. So we have a few things that we know for certain are causing the atmospheric carbon dioxide levels to increase, which thus in turn causes the ocean carbon dioxide to increase. We have the burning of fossil fuels. Since the Industrial Revolution, we have added 400 billion, with a B, tons of carbon to the atmosphere through the process of combustion, just burning our coal, burning our oil, burning our natural gas. All of those things are adding tons and billions of tons of carbon dioxide to the atmosphere. It didn't happen like an even amount per year. This is exponentially increasing as our hunger for more energy, especially in countries like the United States and China and India, as we use more and more energy, our carbon footprint gets bigger and bigger, and so we're putting more and more carbon dioxide into the atmosphere through this process. Another process that's a huge contributing factor is deforestation. And this is going on in Indonesia. It's going on in the Amazon. It's going on pretty much anywhere where they need to clear land. But basically, anytime we are cutting down or burning trees, that's going to produce more CO2 because it also reduces the ability of the biosphere to remove that carbon dioxide from the atmosphere through the process of photosynthesis. So if we don't have the trees removing as much and we're eliminating those sources or those organisms that are able to help us cut back some of the CO2 in the atmosphere, we're like double whammying it. Not only are we adding more, but we're also reducing our ability to remove it from the atmosphere. So 2 major causes that are pretty significant. Okay, almost done, guys. Sorry, this is a marathon session tonight. I guess it's probably not tonight for you, but it's tonight for me. Okay, so let's look at some consequences of this. So the one that we talked about earlier was coral bleaching. So all of those corals that were bright and full of life, they had the algae growing on them, when it gets too acidic, or the oceans get too warm, and as the carbon dioxide gets absorbed by the oceans, it's also warming it. We didn't talk about that earlier, but that's another consequence of it. And as it gets warmer, these coral cannot survive, and they expel all the algae, which is the tiny microorganisms that live here and keep it healthy, from their surface, and then they turn white. Sometimes they recover, sometimes they don't. As soon as they go all white and don't recover, that reef is dead. So that's when we see huge expanses of dead coral reef with no living organisms in them. They are like ghost towns, or they have just the same thing, the same algae that grows. Not a healthy, vibrant coral reef system. Okay. The other thing is shells and skeletons cannot form. Some shells or skeletons may actually not just not form, but they may dissolve as it gets more acidic. The fact that it's affecting the shells and skeletons means that these organisms have to expend more energy on sustaining them and building them, which means they aren't going to be putting energy into reproducing. So we have a decrease in population size because reproduction rates go down. Also, we have impaired senses, and you didn't get to see the video, and I wish I could show it to you guys, of the clownfish experiment where they put 2 clownfish in, or man, it might have been the same clownfish in 2 different samples. I can't remember now. It's been a couple years since I've seen it. And the clownfish aren't supposed to be brave and go out. They're supposed to stay near their home. But when they have more acidic water, more carbon dioxide in the water, they lose their ability to find their home, and they wind up wandering further away, which means then they're more susceptible to prey. That's just a few of the consequences. There are so many more consequences that I'm sure some of them that we don't even know yet. Okay? It's kind of alarming when you start to think about it. All right, let's tie ocean acidification to the carbon cycle. Complete the questions in your packet while we watch the video. There are 7 more questions, okay? So this is only a 3-minute video. We are almost done, okay? I'll make this big. I sure shut my video off. I'm so sorry. Oh well. Okay. Okay, so I might suggest you rewind that and rewatch that to catch everything that they talked about. Most of the things naturally occurring, we have decomposition and volcanism as the two main things the video talks about, putting carbon back into the atmosphere, and as well as into the ocean, we have decomposition and weathering are the two main ways that it talks about in that video. So just making sure you don't overthink that one too much, okay? That is our last slide. So in the space below, on your packet, it says, explain how humans are contributing to ocean acidification. It doesn't have to. Are contributing to ocean acidification. Be sure to include the 4 spheres as well as photosynthesis and cell respiration in your explanation. So it's not too long of a spot there, but please make sure you are thorough. If you need more space, just right on the other side of the paper, there's plenty of space here for you to jot this down. There is no test. This was obviously designed for in-person where we were having tests. And this will actually wrap up what we're doing for Unit 2. So we didn't get, at least we finished this before the end of the semester. We didn't get to Unit 3 yet, but that's okay. We will come back in January and do that. We will be doing a project for our final. I know other teachers are doing other things, so if you're watching from a different teacher's class, listen to whatever your teacher is giving you as your final. I think there's at least 3 different things that I've heard going on. So there's no one final for everybody. But I do hope that this has resonated with you and that it inspires you to think a little bit more carefully about what kind of carbon footprint you're leaving and what sort of impact it might be having to things that you typically wouldn't think of, like the butterfly snails and our tetrapods, I think is what they were called, the salmon, the bears. I mean, when we think of global warming and climate change, we think of the polar bears on the little tiny ice caps. It's so much bigger than that, and hopefully this is inspiring some of you to think differently and maybe become a little more involved with how to fix this. So thank you for bearing with me. I realize this was a really long notes session, even though there wasn't that much to go over. But if you have questions, bring them to class. This is a hefty topic, and I wish we had the time that we would normally have to go over it. So have a great night or day or whatever time of day you're doing this. For me, it is 7:15 on Monday night because I had major issues with Screencast-O-Matic today. So I know I always have issues with things. It's technology. You either love it or you hate it. So there we go. I'll see you guys in class. Have a great rest of your day.